Hello, everyone. Thank you for joining my presentation today. My name is Yinghui Zhang, and I am here on behalf of my co-authors Tailin Chen, Yuchen Zhang, and Ziyu Fu from the University of Exeter and the University of Essex. Today, I'll be presenting our work titled Enhanced Multimodal Hate Video Detection via Channel-wise and Modality-wise Fusion. In this talk, I'll start with the research background and motivation that led to this study, followed by the major contributions we've made. I'll then walk you through our methodology and the benchmarks used to validate our approach. Finally, I'll share our experimental results and the conclusions we've drawn from this work. With the increasing popularity of platforms like TikTok and YouTube, video has become a dominant medium for information sharing, providing opportunities for engagement but also serving as a vehicle for spreading hate content at an unprecedented scale. However, hate speech in videos is often conveyed through subtle cues, such as insinuation or satire, making it difficult for traditional, text-based analysis to detect, especially since these expressions may not always be explicitly aggressive. Many current methods rely on a single modality, like text or image, which limits their ability to capture the rich, complex interactions in video content and lacks the depth needed to understand the interplay between video, audio, and text. Although multimodal methods that combine audio, video, and text offer a more holistic understanding, current fusion techniques still struggle to capture the temporal dynamics and intricate interactions between these modalities effectively. First, let's look at the limitations of current methods. Currently, the HateMM dataset is the only existing dataset for multimodal hate detection, and it relies on a simple fusion method by concatenating features. This basic approach restricts the model's ability to capture the intricate relationships between different modalities, such as video, audio, and text, which are essential for accurately identifying hate content. To address these limitations, we introduce CM Fusion. Our model applies advanced fusion techniques along with temporal cross-attention to better capture dependencies across multiple modalities. This innovation allows us to extract more meaningful and nuanced features, as shown in the UMAP visualizations below. While some recent multimodal approaches have started to include audio and video features, they typically rely on simple late fusion techniques, as seen in Fig 1a. Here, features from different modalities are directly concatenated, resulting in intertwined and less distinguishable feature spaces for hate and non-hate content. To address this gap, our research proposes a more advanced fusion mechanism, channel-wise and modality-wise fusion, or CM fusion. This approach not only captures the temporal dependencies between video and audio streams, but also enhances feature separation, as shown in Fig 1b. This clearer separation demonstrates the effectiveness of our approach in distinguishing hate content from non-hate content more accurately. Our contributions are threefold. First, we leverage temporal cross-attention mechanisms to enable effective interaction between video and audio modalities. This allows our model to capture complex and nuanced features across these different data types. By harnessing the temporal correlations between video and audio streams, our approach enhances the model's ability to learn more discriminative feature representations. Second, we introduce advanced fusion techniques, specifically channel-wise and modality-wise fusion. These techniques help us better aggregate feature embeddings from individual modalities. As seen in our feature space visualizations, our fusion module generates distinct representations, which effectively enhances the separation between hate and non-hate content, an essential aspect for accurate hate video detection. Finally, we validate the superior performance of our model, CM Fusion, by benchmarking it against 5 widely used baselines. Our CM Fusion model is composed of 3 main modules: the feature extraction and processing module, the temporal cross-attention module, and the fusion module. First, in the feature extraction and processing module, we extract features from video, audio, and text using pre-trained models. These features capture essential information specific to each modality, which sets a solid foundation for the subsequent cross-modal interactions. Next, we have the temporal cross-attention module. Since both video and audio data have strong temporal characteristics, we apply temporal cross-attention to align these two modalities. This enables the model to capture cross-modal dependencies over time, allowing it to recognize synchronized patterns and complex interactions between the audio and visual sequences. This step is crucial for improving the model's understanding of time-dependent features, which are often critical in detecting nuanced hate content. Finally, the fusion module is divided into two parts, channel-wise fusion and modality-wise fusion. In the channel-wise fusion, we use a multi-head linear layer to process features from each modality independently, unifying their dimensions and ensuring a harmonized fusion process. The modality-wise fusion includes a feature weight module and a gated mechanism, which adaptively selects and highlights the most relevant parts of the features for the task. This helps fuse information from all three modalities, video, audio, and text, into a comprehensive representation that improves classification accuracy. In summary, these modules work together to enhance the model's capability to detect hate content by leveraging synchronized, modality-specific, and adaptive feature representations. For our benchmark experiments, we set up the environment as follows. We used Python and PyTorch for model development, running on an NVIDIA L40 GPU. We applied 5-fold cross-validation, with each fold consisting of 70% training data and 30% test data. Our batch size was set to 64, and we trained for a total of 40 epochs. In terms of baseline models, we tested several architectures for each modality. For text, we experimented with BERT and ChatGPT 3.5. For video, we used the VIT, Vision Transformer, model, and for audio, we used MFCC features. One of the key baselines we used for comparison was the HateMM model, which combines text, video, and audio features. The figure 3 illustrates the structure of the HateMM model. Each modality's features are processed through its own model, followed by a fully connected layer, and then passed through a fusion layer and a classification layer. This slide presents the experimental results, comparing our CM Fusion model with 5 baseline models. As shown in Table I, CM Fusion achieves the best performance across almost all evaluation metrics, particularly excelling in F1 score and recall. Compared to single-modality models like BERT, VIT, and GPT 3.5, CM Fusion demonstrates a clear advantage by integrating text, video, and audio modalities. Although GPT 3.5 achieves slightly higher precision, its recall is significantly lower, indicating a trade-off that limits its overall effectiveness. Single-modality models like BERT, VIT, and MFCC are constrained in their ability to capture complex multimodal information, which impacts their performance. When comparing HateMM to CM Fusion, we see that CM Fusion consistently outperforms HateMM across all key metrics. Specifically, CM Fusion achieves an accuracy of 82.3%, a 2.49% improvement over HateMM. In terms of F1 score, CM Fusion reaches 0.86, surpassing HateMM's 0.841, which is crucial for ensuring a balanced detection of hateful content. Most notably, CM Fusion achieves a recall of 90.8%, a significant improvement over HateMM. High recall is essential in real-world applications, where undetected hateful content could have serious social and legal repercussions. This enhanced recall helps in more effectively identifying and removing hateful content, promoting a safer online community. Here is the results of our ablation study, shown in Table 2, where we analyze the impact of different fusion strategies and model components within CM Fusion. Starting with two-modality fusion, we observe that combining two modalities, such as video and audio or text and audio, provides reasonable performance. However, these configurations lack the comprehensive integration found in three-modality fusion. In three-modality fusion, using all three modalities results in a significant improvement, with an accuracy of 0.809 and an F1 score of 0.847. This highlights the advantage of integrating information from video, audio, and text. Introducing temporal cross-attention, TCA, further enhances temporal alignment across modalities. However, while achieves an F1 score of 0.827, its accuracy remains at 0.785, indicating that temporal alignment alone is insufficient for maximizing overall performance. Next, we look at the impact of channel-wise and modality-wise fusion, CMF. This model achieves a strong F1 score of 0.85 and a high recall of 0.9, effectively capturing a wide range of positive instances and demonstrating its strength in multimodal integration. Finally, our CM fusion model, which combines element-wise addition with advanced temporal and modality fusion techniques, achieves the best results with an accuracy of 0.823, an F1 score of 0.86, and a recall of 0.908. This emphasizes the importance of combining sophisticated fusion mechanisms to fully leverage the potential of multimodal information. In conclusion, we introduced the CM Fusion Framework, a new multimodal model designed for hateful content detection. By utilizing temporal cross-attention between video and audio, our model effectively captures temporal correlations, providing robust temporal modeling. Our approach integrates channel-wise and modality-wise fusion, aligning features across modalities and applying adaptive weights, which significantly improves classification performance. Through extensive experiments, CM Fusion demonstrated superior performance, surpassing 5 common baselines, including single modality, large language models, and other multimodal models. Our ablation and case studies further validate the model's design, showcasing the potential of advanced fusion techniques in enhancing hate video detection. Thank you for your attention and interest in our work.